Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm going to talk about joint work with Pawan from Iowa State and Kanat Thangwon San and Kunlung Wu from IBM Research. So, why are we talking about graph streams? The motivation for many of these streaming models, I think, is monitoring. Monitoring, in this case, a very large graph that's changing dynamically. For example, if you think of entities in a network, say IP addresses, and the communications between them, that's a potentially massive graph with lots of edges coming in as time progresses. Every time there's a connection, there's an edge. Right? So the point about this is an event in this system is an edge or perhaps a hyperedge. So we want to continuously maintain some property of this large evolving graph. In this case, I'm going to talk about local property. And what I mean by local is that it's within the one neighborhood of a vertex. Okay, let's say count the number of subgraphs within the certain specific subgraphs in the one neighborhood. So I'm going to focus on basically small machines and big data. And in this case, basically all the algorithms that we talk about can be deployed on a single machine, reasonable resources. It also is one pass-through data, just like the classic data stream model. And the good thing about this model is when it works, then it's good for a lot of cases. It's good for parallel computing, it's good for disk resident data, and so on and so forth. So in this case, this is the model. And we've also have some follow-up work on how to use a multi-core machine effectively. For example, you can process really large graphs, like 167 gigabytes with 10 billion edges in about 1,000 seconds on a 12-core machine. All right, so the focus of this talk is going to be on triangle counting. Okay, so the problem is very simple. So, do you have a pointer here?
Yes, the screen.
Green.
Just turn it on the side.
Oh.
There's a button on the side.
Oh, okay. Thank you.
Now.
Oh, thanks. Oh, it's okay. Oh, thanks. Okay. So if you take this graph, we want to count the number of triangles 1 and 2 and 3. Okay, very simple problem. Okay. And why are we concerned with triangle counting? First of all, it's a very basic structural property of a graph. Most of the times when people want to do a structural analysis of a graph in social networks and so on, number of triangles seems to come up. All right. In particular, there's a metric called Transitivity Coefficient, which is used a lot in social network analysis. And that's defined to be exactly the number of triangles times 3 divided by number of connected triplets. Meaning how often are 3 people who are connected to a single person via a single person also form a 3 clique. How friends of friends are they connected to each other. So, and then there's also a property called the clustering coefficient, which is also very related. And in general, there have been many applications. For example, Becchetti et al. Talked about web spam detection. And they showed that a larger than usual number of triangles is the indication of a web spam in a web graph. Okay. So if you want to go to higher order cliques, in biological networks, there is a graph summarization technique that's called as network motifs or graphlets. What it essentially is a vector consisting of the number of occurrences of different types of subgraphs in a large graph. How many wedges, how many triangles, how many cliques of size 4, and so on. And that's a vector that's used to describe the graph. That's called a structural summary. All these are local properties in our sense. Okay, so, Okay, here's our contributions. We give a new sampling algorithm for graph streams. I'm going to describe it in a moment. And we show it can be applied to counting number of triangles. It can also be used to sample a random triangle in a graph. These two are closely related problems. And then we show extensions to higher order cliques, K4 and K5. Apologize about this. I made PowerPoint on one machine, I moved it to another machine, and something happened. So sorry. And then we also can go to directed graphs, and we show some experimental results. So one thing I want to say is I think this is a fairly flexible technique, a sampling technique. And so before going to the technique, I want to briefly tell about prior work. There's a lot out there on sampling, on counting triangles in offline and online models. Started off with the streaming literature started off with this paper in 2003, which reduced the problem to for computing frequency moments in appropriately defined streams. And then there was a lot of follow-up work, 2005, Johari and Gotsi, Puriol et al., 2006. Both of them were sampling-based. And then there are sketch-based estimators. More recently, Guha, An, McGregor, Kane et al., Manjunath et al., all these are sketch-based algorithms, meaning that they work under insertions and deletions, whereas we work only under insertions of edges. There's also a more recent sampling-based algorithm by Seshadri et al. Okay, so these are all different from what we described, but if, the exact details we can talk offline. So in the non-streaming batch context, there is also work by, in the map-reduce model especially, Pag and Chourakakis, Suri Vasilvitsky, and so on. Okay. So a graph model, simple graph. Let's say there are n vertices and m edges. We want to estimate tau of G, which is defined to be number of triangles in G. Okay. And our arrival model is that edges can come in an arbitrary order. Okay. An adversary can decide how the edges arrive. There's also a different model called incidence stream model. By the way, this is called adjacency stream model, what we consider. In the incidence stream model, it's a little easier because it's assumed that all the edges incident at a vertex arrive together in some way. Okay, it's like the incidence graph presented, adjacency list of a graph presented one list at a time. So, but what we talk about is arbitrary order. So there's a close connection between sampling and counting as follows. Okay. Suppose somebody gave me a procedure A, which did the following on graph G. So if the procedure succeeds, it may not succeed sometimes. If it succeeds, then it's going to return a uniformly randomly chosen triangle from the set of all triangles in the graph. Okay. Sometimes the procedure might fail, and it will say, I don't know, I don't have an answer. Suppose you had a procedure like this. You can use a procedure to count the number of triangles in the graph in the following way. So with this procedure, the probability that it succeeds in returning a triangle, doesn't matter which one, the probability that it succeeds is proportional to the number of triangles in the graph. Okay. And so here is a parameter, the probability of this success of this algorithm. And if you can estimate the parameter, then we are done. We counted the number of triangles in the graph. And the estimation of a parameter can be done in a very straightforward manner. Just repeat this algorithm many times and use the fraction of number of times it succeeded, fraction of time it succeeded, use that to estimate the number of triangles. Okay. So if you can do counting, so if you can do sampling in a uniform way, you can do counting. All right. So the only thing is the accuracy of the estimate depends upon the probability that A fails. Okay. If it fails too often, then it's not going to, you'll need a lot of repetitions to get a good estimate. So I'm going to go through a couple of sampling algorithms, sampling a random triangle from the graph. Okay. Perhaps the most basic one, simplest one, is to just select a triple at random, UVW, okay, from the set of all n choose 3 possible triples. And then when I'm observing the stream, I only look for this particular triple. If it happens to be a triangle, great, I succeeded. Otherwise, I didn't succeed. So if this algorithm once succeeds, it's clearly going to return a uniform random sample from the set of all triangles. But it's not going to succeed unless the graph is really dense in number of triangles. The number of triangles must be close to n choose 3. Right? So there is a better sampling algorithm. Again, this was used in a paper by Buriol et al. 2006. And what they said was, first, let's at least fix one edge in the graph. Okay? Let's sample a random edge in the graph, UV, and then you sample a random third vertex, W, from the set of everything but U and V. Now I wait to see if U and V and W form a triangle. Okay? So this is certainly going to succeed more often than algorithm 1. So given in this background, I'm going to describe our sampling idea. So in neighborhood sampling, the first step is to just choose a random edge R sub 1 in the graph, uniformly chosen from the set of all edges. Okay. And then we say that two edges are adjacent if they share a vertex. So what we do is, once we choose R sub 1, from all the edges that come after R sub 1 and are adjacent to R sub 1, I choose another random edge. Let's call it R sub 2. Okay. So R sub 2 is chosen from a substream that's adjacent to R sub 1 and comes after R sub 1. All right. So that's it. Once I have R sub 1 and R sub 2, I have two edges that define a potential triangle, and I wait for the third edge in the triangle to come and complete it. If it completed a triangle, then good, I'm lucky. Otherwise, I fail. The procedure fails. Okay. So one thing to note is that this procedure can be done in a streaming fashion with just a constant number of words in a straightforward manner, because choosing a random edge R sub 1 can be done in reservoir sampling. And once you choose R sub 1, then you have a reservoir sampling on the substream to get R sub 2. And so everything is constant number of words. Okay. So now the question is, there are two questions. One is, how likely is this to succeed? And there's one more question, which is, does it really return a uniform random triangle, uniformly chosen random triangle? So in fact, this algorithm is not going to return all triangles with the same probability. Okay? Some triangles are going to get higher likelihood of getting chosen, some of them lower. So that's a sampling bias that we'll have to overcome somehow. So to give an example, here is a graph with 11 edges, and the edges are numbered according to the order in which they arrive in the stream. So let's say this one came first, then followed by this, E4, E5, E6, and so on. Okay, so given our sampling algorithm, we focus on this triangle E1, E2, E3. What is the likelihood that this triangle is chosen by our algorithm? So for that to happen, we need two events to happen. One is that when in our random sample R sub 1, chosen uniformly from the entire stream, we need to have E sub 1. Okay. If E sub 1 was not there, then R sub 1, then we won't get this triangle. So we do need R1 equal to E sub 1. And if you look at what's adjacent to E sub 1, it's E2 and E3. Among these two, if I choose E3, then I'm out of luck, because E2 will have already gone by, and I won't be able to complete the triangle. So I have to choose E2. So probability that R2 equals Z2 given R1 equals E1 is actually pretty good. It's just 1/2 because E1 has only 2 edges coming afterwards and neighboring to it. So the entire probability of choosing E1, E2, E3 is 1 divided by 10 times 1/2. So it's 1/20. Okay. Now let's take a different triangle, E4, E5, E6. So this triangle over here. So likelihood that we get this is, first of all, we're going to choose E sub 4 in our first level random sample in R sub 1. R sub 1 should be equal to E sub 4. And among all the edges adjacent to E sub 4, we need to choose E sub 5. Okay. Now E sub 4 is a popular edge in that there are 7 other edges incident to it. All these 1, 2, 3, 4, 5, 6, 7 edges are all incident to E sub 4. And they all come after E sub 4. Okay. Among this group of 7 edges, we need to be lucky and we need to choose E sub 5 and then we are through. So the probability of selecting this triangle is actually going to be 1 divided by 70. This is 1 divided by 20. Okay. So now an algorithm that's going to give arbitrarily different probabilities to different triangles is not of much use in general, okay, for counting problems. So, but we thought let's do this anyway. And then what came out useful was that you can actually track the bias that this algorithm is going to give to the triangle that we finally chose. So in particular, let's define cioffi to be, for an edge E, number of edges that were adjacent to E and that followed E. Define that to be cioffi. Okay. Once you have that, let's look at what happens to C of E1 in this case, this edge E1. According to this definition, C of E1 is just 2. There were 2 edges that came in. And if you look at E4, C of E4 happens to be, excuse me, it's not 2, it's 7. So that's a mistake. That should be 7. Okay. So, and you know, if you look at the probability of choosing triangle E1, E2, E3, it's exactly equal to 1 divided by 10 times 1 divided by C of E1. And the probability of choosing this triangle is equal to 1 divided by 10 times 1 divided by C of E4. Okay, so the bad thing is these triangles are coming out non-uniform, but the good thing is we can keep track of what's the bias that we are going to give against this triangle. So in general, it's easy to see that for a triangle T, where E is the first edge in the stream, the probability of choosing it is a constant number across all triangles, 1 over m, times 1 over C of E, which is specific to this edge E. Okay, great. So from there, the rest actually becomes straightforward. So if you were interested in sampling a triangle uniformly at random, and you had a procedure which was non-uniform, you can just use rejection sampling, where you reject the sample that you got with probability proportional to the bias that you gave for this triangle. Okay. Very, very popular technique. And the nice thing here is we know the bias. We computed it in an online fashion. Just do that. So for sampling uniformly at random, we can just do rejection sampling. For counting triangles, we can do something even better. We can actually use the neighborhood sampling as described and compute online the bias for this triangle that we got. And you can incorporate the bias directly into the estimator. Okay? So, in fact, the entire algorithm is actually very simple for counting triangles in a graph. So at the first level, you have R1, which is a random edge in the entire stream. And then let E sub 1 be the edges that arrived after R1 and adjacent to R1. R2 is randomly chosen edge from E1. And C1 is the size of E1. Okay. Now, we wait for this triangle to be completed. R1 and R2 define a potential triangle. If it's completed, then I return C1 times M. C1 is, in some sense, the bias against this triangle. That times M, I return that. And if this triangle was not completed, I return 0. Okay? That's our estimator, very simple. Now it's easy to prove the properties of the estimator, actually. Then if x is the return of the algorithm, then it's the expected value of this x is equal to the number of triangles in G. Very simple proof. And then you can just run a whole bunch of independent estimators and take the mean of all of them, and you're going to get a good approximation. Of course, the key thing is how many estimators do you need? That happens to be number of edges times the maximum degree divided by number of triangles. Okay. Now, you might be thinking, this is crazy. We want to estimate the number of triangles, but the number of times you have to repeat it is inversely proportional to the number of triangles. Well, there's actually not much you can do about this in some sense, because in the worst case, these algorithms have all got to take a lot of estimators, because to determine if a graph is triangle-free or not in the streaming model itself, in the worst case, takes order n square space. Okay, but this is better than previous algorithms, because it used to be either maximum degree square for one of the algorithms, Johari and Goetze, or it was the number of vertices times number of edges for the algorithm of Buriol et al. Okay, so it's better than, it quite significantly improves upon the space taken by the previous algorithms. All right, so the space complexity is clear because it's basically equal to, equal to number of estimators that you take, and every estimator is constant. For the time, question is, if you run R estimators in parallel, does it take order R time per update? That would be pretty bad. So we have some methods here where we use bulk processing. You do a whole bunch of edges at one time, W edges at one time. And because of the random sampling nature of this whole algorithm, this W edges can be processed much faster than processing them one by one. So in fact, if you choose W equals order of R, then the entire batch of W edges can be processed in W time. So order 1 per edge, no matter how many estimators you have. Okay. All right, so I guess, again, sorry about this notation here. It really was R sub 1, R sub 2. Something happened to it. So the same thing can be extended for 4 cliques, very natural manner. Now the algorithm that you can make up is pretty much what I have over here. You sample a random edge, and then from the neighborhood of this edge that we sampled, I sample another random edge R sub 2, and from the neighborhood of R sub 1 and R sub 2, I sample another edge, R sub 3, and finally what I have is a potential 4 clique, which I wait to be completed. Okay. Now this doesn't quite work because you need some special cases which this does not take care of, but we can, there is a ways to incorporate that also. And overall, this very simple natural algorithm actually gives the current best bounds for counting the number of 4 cliques in a graph. Okay. So in some ways, it reminds me of sticky sampling in the case of stream processing. To find frequent elements, you randomly choose an element and then count the number of reoccurrences of this. Here in graphs, we choose a edge randomly and then only now stick to the neighborhood of this edge. Okay, and that way we're going to get a little better space bounds. All right, the extensions I think are very interesting. Transitivity coefficient is trivial because most of the work is actually counting number of triangles. You can extend this to sliding windows because it's based on random sampling, and random sampling on sliding windows is a well-studied problem. You can just use those techniques here. Nice thing is you can convert this into, you can manipulate this in a lot of ways, directed 3 cycles. That's pretty easy because, after you selected R sub 1, you make sure that R sub 2 that you select has a potential of forming a directed cycle with R sub 1. Okay, so you only look at things that are either coming into the tail of R sub 1 or going out from the head of R sub 1. So you can do directed tree cycles also. And I don't know of any previous work on directed tree cycles in a streaming model, but so you can use this one. And then you can have other constraints. For example, you might have a temporal constraint which says how many instances where you had A connected to B, followed by, in time, B talking to C, and followed by, in time, C talking to A. So it's not a graph anymore. It's something else where there is time involved. You can even count the number of such patterns because of the sequential nature of the sampling that we have. Okay, so just a few words about experiments. I'm almost done here. So we implemented this on a bunch of graphs. Here's an example Orchid graph with more than 100 million edges and a pretty high large max degree. And we found that just with 1,000 estimators, we got a relative error of 5% on a single machine. It took 50 seconds. Out of 50 seconds, 33 seconds was for I/O. So it was really very, very practical. If you use 1 million estimators, meaning a few megabyte of memory, then you get the error down to, relative error down to 1.5%. And it takes still a very reasonable amount of time. So I have a couple of graphs. Basically, if you multiply the number of estimators by 8,000, the time goes up by a factor of 10. Okay, according to theory, the time should be the same, but I think this is because of the caching effects. With 1,000 estimators, it was much faster, and so, all right, so I'm just going to skip all this. So to conclude, what I presented is a general sampling method for estimating graph patterns which lie within the one neighborhood of a vertex. Okay, so it can work for small size cliques. You can throw in a bunch of special cases and it still seems to handle it and can take care of it, like temporal constraint, edge directions, and so on. And then I think of this as something like sticky sampling for graph streams. So hopefully it will have more applications for such questions. The technique is very simple. Sample within the neighborhood of currently chosen edges. And what you have is a bias sample, but you can maintain the bias online and incorporate the bias into your final estimator. Okay. Then we have fast implementations. So in particular, we have a multi-core implementation which uses a bunch of the techniques from Carnegie Mellon, like Silk, especially the cache oblivious algorithms. And for example, a graph of 10 billion edges, a synthetic graph, which takes 167 gigabytes, can be processed in 1,000 seconds on a 12-core machine. Okay, so that's all I had to say. If you want the paper, then please send me an email, or you can visit my webpage. I have a link to that. Okay, thank you.
Thank you very much.